So the questions for chapter 11.3 of the Oxford published AQA Physics Year 1 textbook. These are questions on stress and strain, and I'm going to answer these 4 questions. Okay, so question 1 asks us to calculate the tensile stress in a wire. Diameter, we're told, is 0.25 millimeters, and the tension in the wire is 50 newtons. Just to remind ourselves, there were 2 terms that were defined when we were looking at trying to deal with materials and the properties of materials in terms of their deformation with forces. The first of these, which is mentioned in the question, is tensile stress. And tensile stress is defined as the tension per unit area. So it is the tensile stress is tension over cross-sectional area. And the other property is tensile strain. And this is defined as the extension over the original length. In that the diameter is 0.25 millimeters, that is equal to 2.5 by 10 to the minus 4 meters, and the tension is 50 newtons. The area is pi r squared, so the cross-sectional area would be equal to pi times a half of 2.5 by 10 to the minus 4 squared, which gives us the area is equal to 4.91 times 10 to the minus 8 squared, and we know that the stress is defined as the tension over the area. That gives us the stress is equal to 50 divided by 4.91 by 10 to the minus 8. So before we work out the answer using our calculator, we can very quickly see that we're expecting a number that's going to be very large, in the order of 10 to the 8 or 10 to the 9. So 50 divided by 4.91 times 10 to the minus 8, that gives me an answer of 1.018329939 by 10 to the minus 9 newtons per meter squared, or pascals. Obviously, you don't write the answer out like this. We've been given 2 significant figures, so we could write the answer as 1.0 by 10 to the 9 minus 9, 10 to the 9 pascals. Okay, so you never write out a number like this, even if it hasn't asked for significant figures. You look at how many significant figures you were given in the question, in this case 2, and that's the number that you should use in the answer. Okay, the next question, we're told a metal wire, the diameter is 0.23 millimeters. Its original or unstretched length was 1.405 meters. Suspended vertically from a fixed point. 40 Newton weight has been applied from the lower end of the wire, resulting in an extension of 10.5 millimeters. Calculate Young's modulus. So the numbers I was told was that the diameter is 0.23 millimeters. So that's 2.3 by 10 to the minus 4 meters. The original length, unstretched length, was 1.405 meters. There's a 40 Newton force applied, and we're told that the extension is 10.5 millimeters. So that is 1.05 by 10 to the minus 2 meters is the extension. And we're asked to calculate Young's modulus. Now, Young's modulus is defined as the ratio of the stress to the strain. And we've got two choices here. We can either work out the stress and the strain individually and then divide the answer for the stress by the strain, or using the algebra, we know that this is equal to tension times length divided by cross-sectional area times the extension. I'm going to do this by working out the stress and the strain individually. So here I've got that the stress is equal to tension divided by cross-sectional area. The area is equal to pi r squared. That's pi times 2.3 by 10 to the minus 4 over 2 squared. That gives me an answer of stress of 4.15 by 10 to the minus 8 squared. Therefore, I have the stress is equal to 40 divided by 4.15 by 10 to the minus 8. The stress is equal to 9.63 by 10 to the 8 pascals. The strain is equal to the extension over the original length. That gives me the strain is equal to 0.05 by 10 to the minus 2 divided by the original length 1.405. And that has no units as it's a ratio of lengths. To give me an answer of 7.47 times 10 to the minus 3. Therefore, Young's modulus would be 63 by 10 to the 8 divided by 47 by 10 to the minus 3 to give me a value for Young's modulus of 1.29 times 10 to the 11, and the units are pascals. Now, the thing we need to think to ourselves is how many significant figures should I use here? So, you see, I've got more significant figures in some of the numbers, less in others. 3 here, for example, 2 here, for example. The best rule of thumb is you use the same number of significant figures as in the smallest that's given in the question. So here I've got 2 significant figures. So I'll give my answer to 2 significant figures. Now, as I said, there were 2 approaches to this. I could either use the equation and just put the numbers in here, or I could work out the stress and the strain separately. I chose to work out the stress and the strain separately. It means that in an exam, you've shown clear understanding of what it is you're doing, but also it means that if you get the stress calculated correctly, but you've made an arithmetic mistake working out the strain, you've still got a good chance of getting most of the marks. You may also get the marks from substituting into the equation, but it is possible that you might pick up more marks by separating it out like this. The disadvantage of doing it this way, obviously, is that here you keep full precision until you do the rounding at the end, although in this case it gives you the same answer to 2 significant figures. Right, now question 3. Here the steel wire, the length is 2.5 meters, diameter 0.35 millimeters, supports this weight. And again, we're calculating the stress and we're calculating the extension. In this case, we're told what Young's modulus is. So if I write out what I'm told, to start with, I'm told that the length is 2.5 meters. I'm told that the diameter is 0.35 millimeters, which is equal to 3.5 by 10 to the minus 4 meters. I'm told the force is 90 newtons. I'm looking to calculate the tensile stress. I'm also looking to calculate the extension. Extension I can write as delta L. But I'm also told that Young's modulus is 2.1 to 10 to the 11 pascals. Okay, so let's do part A. We're looking to calculate the tensile stress. So the cross-sectional area, which is pi r squared, is equal to pi times 3.5 by 10 to the minus 4 divided by 2 all squared. You should have noticed by now that in all of these questions, and it is the same very often in exams, they don't give you the radius, they give you the diameter, for the very simple reason that diameter is what you would measure using a micrometer or calipers when you were measuring the size of the wire. So that's what you're most likely to get from a measurement, is that diameter. So normally in these questions they give diameter, and you have to remember that you're working at the cross-section area from the radius. So that gives me an answer of cross-sectional area of 9.62 by 10 to the minus 8 meters squared. The stress is equal to tension over area. Let's just rewrite that out properly. So when I substitute in for that, I've got 90 newtons divided by 9.62 by 10 to the minus 8 meters squared to give me tensile stress of 9.3544 by 10 to the 8. So it gives me an answer of, and how many significant figures I'm going to write. Well, looking at the question here, I'm going to write this as 2 significant figures, 9.4 by 10 to the 8 pascals. Then part B, I'm looking for the extension. So the extension, it's used whenever we work out the strain. So we say the strain is equal to the extension over the original length, which gives me the extension is equal to the extension times the length, the strain times the length. But we haven't been given the strain, so we have to calculate the strain, and we can get that from Young's modulus. So Young's modulus tells us that the Young's modulus is equal to the tensile stress divided by the tensile strain. So the strain is equal to stress divided by Young's modulus. So my tensile stress is equal to 9.4 by 10 to the 8 divided by the number I was told in the question, which was 2.1 by 10 to the 11. So put that into my calculator. It gives me an answer of 4.5 by 10 to the minus 3. And remember, this is a ratio of length, so it has no units. And then I have to use that to calculate my extension. That's going to be equal to 4.5 by 10 to the minus 3 multiplied by the original length, which was 2.5 meters, which gives me my extension is equal to 0.011 meters. That's equal to 1.1 by 10 to the minus 2 meters. And we can think to ourselves, does this seem like a reasonable answer? What does this mean? It means that we have an extension of around about 10-11 millimeters. That seems a reasonable answer. So in question 4, we're being asked to interpret the stress strain graph to be able to say something about two different materials, X and Y. So we don't know what the materials are, we're just showing their stress strain graphs, and we're asked to say something about the properties of these materials. So we're asked to say for material X or Y, which of these materials is the stiffest and which is the strongest. So we need to think about what do these terms mean for stiffness and strength. So stiffness. What does stiffness mean? Stiffness comes from the gradient of the stress strain graph. So we get the stiffness of the material, or we can compare the stiffness of the materials from the Young's modulus. Shouldn't say it's. We get it from the gradient of the stress strain graph. So in this case, we can see that X has got a greater gradient than Y. So X has a larger gradient than Y. So X is the stiffest. Then the second property they ask us to talk about is strength. Now, strength, we compare strength from the ultimate tensile strength, stress. So strength is given by the ultimate tensile strength. So for X, that is this point here, and for Y, that's here. So clearly X has a larger UTS than Y, so X is the strongest. Then the third material we're asked to look at, the third property we're asked to look at is brittleness. So which of these materials is most brittle? And a brittle material is one, this is one that snaps without any yield or little yield. And here we can see from the graph that the material that's most brittle is Y. So Y is brittle, and that leaves us with the final property, which is which of the materials is ductile. And ductile means can be drawn into a wire, so we can continue stretching it into a wire. Clearly that's not Y, but here we can see the plastic deformation of X happening after it's passed the elastic limit. So X is ductile. And that concludes the 4 questions.